we come to the final talk in this session, and I'm very excited to introduce the next speaker, none other than my co-host, Dr. Alyssa Peleo-Alampay, Professor of Geology at the National Institute of Geological Sciences at the University of the Philippines, Diliman, and currently the Assistant Vice President for Academic Affairs in charge of quality assurance of the University of the Philippines system. She heads the NanoWorks laboratory, forgive me for that phone ringing, NanoWorks laboratory at NIGS, doing research on fossils to understand the Earth's geologic history. Alyssa is also the faculty in charge of the NIGS UPGAA Geology Museum. She obtained her bachelor's and master's degrees in geology at the University of the Philippines, Diliman, and her PhD in earth science at the Scripps Institute of Oceanography, University of California, San Diego, USA. Dr. Alampay was a Balik Scientist Awardee of the Department of Science and Technology and was awarded as one of the nation's outstanding women in nations science, the prestigious Towns Award in 2007. So Dr. Alampay, take it away.
Thank you very much, Giselle. So not by design, but Alan and I are actually we have complementary talks. Do you see my slide now? Is it visible?
Yes, we do. You could...
the slideshow.
Yeah,
okay.
Load up to the slide.
So it turned out not by design, but it's complementary. I guess it's natural because we belong to the same lab. Alan talked about the big fossils, and I'm going to talk about the small fossils, which is our core competency in the laboratory and actually at NIGS. Magandang tanghali po sa lahat. Abutin na tayo ng lunch. Pasensya na po. Sana po mapagtiyagaan nyo pa yung talks. I hope you can still hang around for the talks and the question and answer later on. I am joined in this paper by colleagues, of course younger than me, by Alan and Azar, Doms, Jaan, Dois, and Debs, all of whom are or were with the NanoWorks laboratory at different times in their lives. Some of them have moved on doing their PhD. So Doms is in Toronto. Jaan has moved on to the National Museum. Dois is now teaching at Ramon Magsaysay in Zambales, while Debs is doing her postdoc in Salamanca after finishing her PhD in Bremen in paleoceanography. So the talk is really about microfossils. So I just made it a little bit more popular by saying that they're tiny marine creatures of the past. Really, it's all about micropaleontology and what we've been doing in the lab in the last several years. So I guess I have to start with this in case there's people in the audience who are not familiar with what fossils are, but I know that most of you are because a lot of the attendees are geologists. So because they're the most tangible records of life on Earth, there's nothing else that's left on Earth except these fossils from rocks. They're also important for dating our rocks and for paleo-environment reconstruction. And I think Alan has shown that in his talk earlier. At the same time, we do correlation using fossils, of course. Correlation being a very powerful tool for geologists, which allows us to match rocks and outcrops and mountains and rivers, I guess, with each other so that we can put together the history of the area. And they're important also because they're our natural heritage. Before I begin my talk, before I go on, let me say that fossils are actually not rare at all. Some people think that they are, but actually they're not. They're actually around us. It's just that it takes a trained eye to be able to see them. Now, why do geologists study fossils? Because fossils are found in sedimentary rocks. And sedimentary rocks actually comprise about 75% of the rocks on the surface of the Earth. So that's why there's really quite a lot of them on the surface. The surface also of the Earth is about 75% ocean And that ocean, at the bottom of it, is sediments, which are also the purview of geology studies, because those sediments actually later on become rocks also. And those sediments are deposited over millions of years on the sea bottom. Some of them end up on land. And so we study those sections by hiking through mountains and doing geological fieldwork and doing sampling. But really, a lot of the things that we see in the fossil record are actually in the marine realm. That's why the large fossils that Alan and colleagues were able to find in those areas in the Philippines are actually quite very, very interesting and very elucidating in terms of our more recent history of the islands. Seafloor sediments are almost, it's a large part of it is composed actually of plankton. No? So it's something that many people don't know, and that's the reason why we geologists study it, because the surface of the earth actually is covered by plankton. And the geologic history of the Philippines is also largely marine. We're a very young terrain, relatively speaking, geologically speaking, and most of that history is actually underwater, under the sea. As Dr. Mario Aureli will attest. So as you can see from this map, I circled here the Biogenus sediments. All the green parts are actually Biogenus, which means these sediments in the oceans are actually made up of skeletons, or the hard parts of these plankton that died, and when they died, they became sediments. Well, not the plankton itself, but the skeletons of these plankton became part of the sediments, to the extent that some of the sediments are actually oozes already of particular either siliceous or calcareous protists that used to live on the surface of the ocean. So these are the Fab Four in Microfossils. These are the superstars when it comes to the minds of the geologists. We use them in order to date rocks. Not date as in, sometimes my students in Geology 1 would laugh when I say date rocks, but it's actually a technical term that means that we give ages to these rocks using these fossils. In particular, coccolithophores and foraminifera are favorites in the laboratories in the Philippines because of the ease in which we can process them. And at the same time, a lot of previous work has already been done in terms of the extent or the occurrences in the sediments. No? So once you see certain types of foraminifera or coccolithophores, they can already be identified. You can already give a numerical age to that particular rock or sequence. Diatoms and radularians are actually also very important, especially in colder areas of the oceans and in some areas where the calcareous, where carbonate precipitation is not ideal. No? So when you have cooler situations in the oceans, you may have more of the siliceous components in the assemblage. Okay, so just to show you that they're quite diverse in terms of geometric form and in terms of composition, especially the foraminifera. They've played around a lot with calcareous composition. Some of them are glassy and some of them have used sands. Actually, even coccolithophores as part of their skeletons. Coccolithophores, as you see on the right, these are SEM photos, they're quite small. And that's also the reason why micropaleontology has also diversified into this field, because of their size. When you have them, you only need the tip of a toothpick, that amount of sample, in order for you to be able to analyze and give the age or the paleo environment of a particular section, because these things are quite small, the coccolithophores. Whereas when you use foraminifera, you really have to wash the sediments, sieve them, and then pick them one by one. So with the coccolithophores, it becomes easier. So they're very good complementary microfossils to study in the sediments. And in the Philippines, a lot of micropaleontology, micro meaning small, and paleontology, the study of fossils, has really been around for quite a while. Even before the Department of Geology and Geography was named in UP Diliman, there was already a micropaleontologist, Professor Gutierrez, Fernando Gutierrez, who also became department chair of that department, which was the precursor for NIGS. No? And so in the early days, I just got images from the internet of these microscopes, but the SEM is actually in our lab. In the early days, they only had really the microscope without having to use electricity, just using sunlight, and so it was very difficult to see the smaller stuff. And so that's why the coccolithophores did not get any focus. No? Micropaleontology has been around because there was a need for micropaleontologists for petroleum exploration to give age dates to the sequences that were coming out when they were drilling rocks in the ocean floor. But at the time, there was not much research drilling going on. It was mostly really for exploration. It wasn't until later when technology was able to come up with stronger microscopes, and now it's become a little bit more cheaper. It used to be the price of these microscopes used to be like Mercedes-Benzes in Germany, very expensive microscopes, millions. Now they're going down to less than million, and so it's become a little bit more affordable for projects to get them. But we now have in our lab also a scanning electron microscope, which allows us to get to take images of these coccolithophores, especially the small ones, and look at their textures and identify them better. All of this also, the progress in the research in micropaleontology would not have happened if we didn't have ocean-going research vessels where scientists can stay for 2 months at a time, like for example, enjoy this resolution, and or 2, 3, 4 weeks, a month at a time in the smaller vessels. These two vessels actually, some of us have been fortunate enough to be able to get on board these vessels. The one at the bottom, the BRP Gregorio Velasquez, used to be actually RV Melville, which was owned by Scripps before, no? Where Dr. Silidum and myself actually graduated by coincidence. And also, I was happy to note that of the 5 speakers, turns out 4 of us were able to get on JOIDIS resolution at some point in our lives, now, which was really a highlight in our careers also. So what are coccolithophores? They're known also as calcareous nanoplankton, so that sometimes you call them nanoplankton or nanos or nanofossils or coccoliths. No? And you'll see why. Coccoliths are actually the component skeletons of these organisms. They're algae. They're like plants. So they're photosynthetic. That's what autotrophic means. So they're marine haptophytes. They have an additional haptonema or the flagella for food gathering and other things. They're microscopic. The spheres or the cocospheres pictured here on the right, these are colorized SEM photos, are about 5 to 100 microns in size, while the coccoliths or the liths, the ones on top there, which are disaggregated from the cocospheres, are only about 2 to 25 microns. So we really need powerful microscopes in order to be able to see these guys. But once you see them, they're actually very nice to look at, and well, I guess it just takes we just love them, but you know, I guess that is relative. No, some people don't like to look down the microscope. So they have tiny bodies which are composed of calcium carbonate or calcite, or they are calcareous, and they're major contributors to carbonate sediments since the Cretaceous and even a little bit earlier. And the Cretaceous period is of course the time when the dinosaurs still roamed the earth. Now, coccolith studies in the Philippines have actually varied in terms of how we collect them. And for a time, especially when I came back from my PhD, I did not have too many resources. There was not much support from agencies, and we were still struggling. And so, sariling sikap, I don't know how you can translate that, but we'd often just hire a motorboat, a banca, and then either dive for it without the scuba, of course, or just go down if it's shallow enough, get the sediments and put it in plastic bags or in containers, or else we'd use the grab sampler, you know, as is pictured here. If we're lucky enough, we get on research expeditions, which we call cruises. They're not actually vacation cruises, but expeditions where you tend to be muddy at the end of the day, because you have to take the mud out of the collecting samplers from the samplers. No? So, and it can be very muddy. You have to sometimes shovel out the mud that comes from the ocean bottom. Very exciting because you know that when you look down the microscope, there are really a lot of organisms that are actually living in them or used to live in them or were recorded in these sediments. It varies. The coring varies, and later on you'll see how big of how big an expedition can be or how small it can be. As I said, it's either you're on a bangka or else you're in a large drilling ship where there are other people specialized to do the work, and you get the samples, and you can readily use a microscope or an SEM on board or other geochemical equipment in order to in real time, I guess, almost real time, look at the samples without having to go back to the lab or to your house for 2 months. We also look at land sections. That's why, as you can see from the picture there are many opportunities, especially when we have graduate classes or undergraduate classes, to look at outcrops. We also have some projects, although it's not usually a priority area. These projects, they do not have very direct resultants, I guess, to humanity, especially now with COVID, But then, in terms of the long-term, I guess, returns to humanity, it's very important for us to understand these fossils because it gives us it puts context into our lives as humans. We also look at sediment traps, and I'll explain what those are later, and also seawater samples, and this is where we pretend to be biologists, but we're not. In terms of certain surface sediments, I'll just give you some examples of what we've been doing in the lab. So this is a project that we did early in our lives because we didn't have money, and so we went to together with Dr. Siringan and some other colleagues. Alan was still quite young then. We went to these bays and started collecting samples. And at the time, it seemed like a lost cause for me as a coccolithophore person because really I needed deep sea samples, but I didn't have a research vessel nor the means to go out and be included in a research expedition, being in the Philippines at the time. But it turns out that these studies were very helpful, not only to train or mentor graduate students, but at the same time, they really are contributions. In the end, I finally found out they were contributions to knowledge about coccolithophores because not many people were looking at the near shore or the marginal sea areas at the time, especially in the low latitude areas in the tropics, because they thought that in the past there was not much change. But of course, when we looked at the sediments and in the water column, we found that there really was diversity, but at the same time, there was a special peculiarity about the assemblages that we were seeing. In particular, it's an oligotrophic, low nutrient conditions, and these coccolithophores really are very good indicators of how nutrient-rich, how cold or how warm the waters are, or how polluted, I guess, is what you can call it, or how much terrigenous sedimentation has gone into the basin. In many of our studies, this particular species, Gephyrochapsa oceanica, pictured here, has always been the dominant guy, which is very different from reports from around the world where Emiliania huxleyi is always the star. But for our studies here in the Philippines, close to shore, when you face the West Philippine Sea, when you're in our embayments, close to almost little ponds, Gephyrochapsa oceanica would be there. And that's why I put the seal or the logo of NanoWorks Laboratory, thanks to, I think it was Adong who put this together. It's actually in the shape of Gephyrochapsa oceanica because sometimes that's most of the time that's what you're seeing. And in the middle, of course, is the sample pic. Based on the studies here, it's Gephyrochapsa oceanica that's abundant. Next would be Profunda, which is also another a strange species, which is not usually counted by many micropaleontologists because it looks like a regular calcite crystal, but actually it's a very nice artichoke-looking coccolithophore. And we looked at the Marinduque Bays, the Buwak and Calancan Bay, because at the time there was a mine spill in some decades past, and we wanted to look at the effect of the mine spill on the assemblage of the nanofossils. And Sunny De Silva was looking, and his student was looking at the forum side of it. And so, of course, very clearly, because not just because of the mine spill, I guess, but or despite that, because of the sediments that were going into the basin, there really was a dearth or an absence, almost an absence of even this very sturdy Oceanica, Gephyrochapsa oceanica in the sediments at the time. Other studies, of course, Alan's study in the South China Sea was one of the most comprehensive surface sediment studies at the time. We were apprehensive when we were trying to design his thesis at the time, whether this was something that could be acceptable in an ISI journal, because these were surface sediments. And as you can see, because of the reviewers thought that it was a good paper because of the extent of the sampling that was done. The samples here were taken from numerous expeditions on board the RV Sone, of which our colleagues were able to invite us on. And so I think this is probably the samples probably came from 3 or 4 expeditions. I was able to be part of that expedition also. The main resultant here is that on the eastern side of the South China Sea, we have a very different dominant assemblage composed of Gephyrochapsa oceanica. But when you look on the side of Vietnam, it's actually Emiliana huxleyi, and that's because there's a very big and very strong upwelling current or upwelling structure that's here off of Vietnam here, especially when the northeast monsoon, the winter monsoon, happens sometime in Christmas time until about February. And so that very strong upwelling signature gives rise to huxleyi, Emiliana huxleyi, which is actually very common in the open ocean. As I said earlier, it's a star. And so by looking at nanofossils, we can really determine, even in the more recent geologic past, how the climate and actually the oceanographic parameters may affect the lives of these and the production of these nanoplankton or these plankton in the waters. Actually, plankton, because they're phytoplankton, they're eaten by the zooplankton or the animal-like plankton, and these plankton are all eaten by the larger animals like fish. So usually we attribute, when we have increase in production of the plankton, we also think, and there is a correlation with larger fish catch. We looked also in Sulusi, and this is part of Debs Tangunan's thesis, looked at Sulusi, and these were Melville cores. And during the study, we were able to correlate the abundances of the nanofossils. When you look at the graph on the right, the abundances of the nanofossils and particular ratios of nanofossils, profunda and oceanica, for example, and look at the trends and see if they correlate with these particular stripes that are going down here. These stripes are actually younger Dryas. These are very cold times in Earth history. And so, cold times in Earth history where to some extent, even if they happened, the trigger is in the northern hemisphere, for example, in the glaciers of the northern hemisphere or the ice sheets in the northern hemisphere. Even here in our tropical areas, at the time, we still get the signal from these northern hemisphere climatic events. So that's also a very big revelation for us, because people, paleoceanographers of the past, thought that there was, in the low latitudes or in tropical areas, there was not much change in temperature. And so you would not be able to see any signal of any of these global climatic events. And of course, we're going through one right now. We're going through the global anthropogenic global warming today. But in the past, before humans came into the picture, actually there were natural cold and warm events that were going on throughout Earth history. And these younger dryas, YD, ODR, and ODS here, are all parts of that Dryas system, where these are cold spells in our recent Earth history. So these are from sediment cores. And these also, the next slides would be results from cores that were taken from an IODP program, IODP cruises on board the JOIDIS Resolution. As I said, some of us were lucky enough to be able to join these cruises, where for 12 hours a day, for example, it was like going back to my PhD days, just looking down the microscope and processing samples and looking at the lovely nanofossils and being able to give ages in 15 minutes, which some of the geophysicists on board couldn't believe that we could do. I actually had to explain what biostratigraphy and fossils were all about and show them that there are actually volumes attesting to our specializations. So this is part of Dom's Gubalia's thesis, where he was able to refine the age dates that we took, or that we analyzed, or we gave during the expedition. So that line over there is this is the age depth plot. After DOMS looked at more samples, this is the resultant age depth plot. I know that you might think that it looks the same, but actually, because of the way that it is plotted, there's not much. You can't see much of the variability. But this is very important for us, because at each point there, then you are able to calculate the ages of the different parts of the core, the sequences, by using a more refined age depth model. In terms of land sections, as I said earlier, some of these marine sediments are now available on land because of either tectonic processes or sea level change. And so in the Philippines, we have a lot of these marine sediments. They're all around you, actually. And in a lot of these sequences, especially if they're deep marine sequences, we can find a lot of these nanofossils. This picture on the right are light microscope photos of index nanofossils that we use. This is from a paper by Debs and Tangunan and others, which is an offshoot of a advanced field class, where we went to Samar. And so this is the Catbalogan Formation, where the age of the formation was refined using calcareous nanofossils. So late Miocene to late early Miocene is the age of this particular formation. Also, in another site, as an offshoot of Geology 170, an undergrad geology course of which Debs was part of, together with members, professors from another lab. They were also able to sample, and Debs analyzed the samples for nanofossils. And because of this, the age, because of the ability to constrain the age of the Balanga Formation, they found that in another part of Mindoro, in the north part also, that there's an extension of the Balanga Formation there. And the Balanga Formation is characterized as having been formed from sedimentation after the Miocene collision of the Palawan-Mindoro block with the Philippine Mobile Belt. So in that sense, nanofossils or fossils can be used to constrain the stories of the rocks, the ages of the rocks, so that we can be more confident in the ages and the stories that we put together. The other way of sampling these microfossils are using these so-called sediment traps. So in the earlier examples, we looked at the sediments already, which have been deposited on the ocean floor. and then even more beneath the ocean floor when you core. But these sediment traps were invented because sedimentologists wanted to collect sediments that were raining down in the water column. So what they do is you leave these funnels. You can have a string of funnels, and I'll show you a schematic in a while. You can leave these string of funnels in the ocean floor anchored using the wheel of a train to the bottom of the ocean floor, thousands of meters, kilometers below. In the South China Sea, for example, we deployed at 4,000 meters, 3,000 to 4,000 meters deep of a water column to the ocean floor. You can leave them there for a year, and then at the bottom, this picture on the left over here shows a grad student taking out the bottles after we've recovered the sediment trap. So that it's a rotating collection cup system, and you can program it to rotate month by month, after you've left it there. And the picture on the lower right here are the collection cups from two traps. And as you can see, there are certain times of the year when you have that black, a lot of the black sediments coming in. So that means that something happened during that time in the ocean column. So here's my favorite animation that's been around for a while. It's just to illustrate to people, what these sediment traps do. And so what happens is that the coccolithophores, whether as spheres or as liths, rain down onto the funnel, and the contents of the funnel are collected into the cups, and we analyze them afterwards. So you now have a monthly and yearly record of the sediments that are present there. So usually when we are on these expeditions, we're in charge of the calcareous nanoplankton, or the coccolithophore part of the sediments. And so we take that out, and we measure the flux, or the amount of the material that goes into the funnels. And so we're able to see, whether it was higher or lower. So in this particular example, which is here which was taken from in the South China Sea, during the northeast monsoon, the shallow trap is getting a lot of the nanoplankton or nanofossils already, because they're already dead by the time they're there. Whereas the deep trap is the one that's getting most of the flux of the nanofossils during the southwest monsoon. And this is largely because of the temperature of the waters at the time. Nanoplankton tend to be not so selective when it's cooler. And so, actually there's usually a lot of them when it's warmer, but in this example over here, the cooler waters are probably coming in from the Pacific, especially during the time of the northeast monsoon. And so it's developing a high productivity area in that particular area of the South China Sea. Another example of how we use these traps and the nanofossils in order to look at the climate of the past or the recent past is by looking at El Nino and non-El Nino years. So this year, 1998 and 1999 to 1999, there was a predicted strong El Nino. And so that's why the sedimentologists from the University of Hamburg, led by Dr. Martin Bissner, went to the South China Sea, and we were able to, some of us were able to go with them. And I believe this was also a cruise where other FIVOLC's geologists were also able to join along with NIG's geologists. And so this particular trap system was put out offshore of the Philippines, literally in the West Philippine Sea. So these are the depths of the traps on the right there. And so I'm comparing the two traps, and you will see that the maroon color is actually very strong. I was a little bit disappointed because turns out there was this one species, Florisphaera profunda, which dominated both seasons, the El Nino season and the non-El Nino season. I was hoping for more variability, but in any case, it was a very strong signal, probably because of the dissolution resistance of profunda, but at the same time, because of the nature of the basin. The South China Sea or the West Philippine Sea is oligotrophic, and so it's a very low nutrient area, and we don't have a lot of diversity there. And so there are a lot of opportunists, so-called opportunists. It happens in life that there are always organisms or entities that can take over the niche of somebody else when they're not looking. And so this is what Profunda does all the time, and actually what Gophyrochapsa oceanica, the other favorite in this area, also does. But for this area, it was Profunda that was dominating the assemblage, no? Whether during El Nino or during non-El Nino, the main difference being that there are a little bit more species present, variety of species present or diversity present in during this time. Now, why did this happen? Why is it that Profunda was still overwhelming the assemblage? We found out later that actually the year 1999 to 2000, we were expecting an opposite effect. Apparently, what happened was that it was not a very strong. The El Nino turned out to not to be that strong, and so the signals were not so in polar opposites of each other. So there was also a lot of rain that happened also during 1999, 2000, and so there was a thick, so-called thick barrier layer. The physical oceanographers call it a thick barrier layer, which actually is really just a freshwater input, most probably from rain or from rivers, nearby rivers, which were putting in a lot of the fresh water in the area. And so it was covering the surface of the sea, of the West Philippine Sea, in that part where we were collecting, and so productivity was low. And it was advantaging the lower photic zone dweller called Profunda in the system. Now, as an offshoot of this work of coccolithophores in the past, or nanoplankton or nanofossils, we had to really look at present day assemblages, the present relatives that live in the ocean of these coccolithophores. And after so much work in nearshore areas, and then sometimes you would be fortunate to be able to get seawater and process it during expeditions, and also asking help from colleagues who were going out to the sea, either using motorboats or using ships. We're able to get quite a lot of samples covering many areas of the Philippines and the surrounding seas. No? And I put in here Hutton, his face, to remind me, why we're doing this. Because, as the adage of most geologists, the present is the key to the past. Really, we cannot say anything about the past or be more detailed about the past if we don't know what's happening today. And so that's why we're trying to study these present day members of the coccolithophores and document it. And so as part also of our public service in a way, and popularizing these tiny creatures, we're now at the last, finally, and Ma'am Carla would be happy, and Ma'am Giselle would be happy to note that we're on the final stages of completing this atlas, and hopefully the UP Press will be able to publish it. We have really nice photos of these coccolithophores, and we think that it's going to be a valuable reference also for our colleagues who are studying it around the world, because there are similar atlases from the Mediterranean, for example, that were produced sometime in the past also. So the next stage in all of this is we found ourselves having so much data. And at the same time, because I was teaching paleontology and historical geology at NIGS, we had this particular chart that all of us memorized since time immemorial. It's called Index Fossils of the Philippines. It looks like this, but this is the revised version. And all of us would memorize it because in preparation for the board exam. It's a very useful reference, because when you're out doing geology in the Philippines, when you consult a paleontologist, you can look at this reference table and sort of understand a little bit, when the paleontologist says it's this particular foraminifera that he or she saw and reported to you, you would know right away what time period you're in terms of the sequences. But actually, when we looked at it more closely, some of them, we were not sure about, whether they were index fossils of particular time periods as it was reported. And so we started looking at the index fossils again, and tried to limit it to discrete, with what we call the discrete index fossils, where that particular species a fossil is only found in a particular period, not over a range of periods or epochs, so that it can be more useful. And then we started expanding that to 2 periods or 2 epochs, and so on. And so Zar Carino is actually the one working on this with me. And so started looking at a lot of literature in the past, geologic reports, even field reports that we had at NIGS, and even theses that past master students have written. And at the same time, we also wanted to put it into a more user-friendly format. And so Zar found MapHub, which is also an open source software and which makes an interactive map for you. And this is sort of the boring look of the index fossils, where, as you can see, the age is there, the Pleistocene, and these are particular fossils that when you see them, you know right away that you're in the Pleistocene. A lot of them now are, when we started documenting them, a lot of them now are calcareous nanofossils. Some of them are foraminifera, large foraminifera. But that is the thing that really struck us, that for the Cenozoic at least, of course, I'm not talking about the upper part of the Pliocene or the Pleistocene, where we have a lot of vertebrate fossils also, that most of the fossils are actually either foraminifera or calcareous nanofossils. And so what we did, so that more people can probably appreciate it, is to try to map it on MapHub. So the list on the left are the fossils that we found documented in journal articles, vetted by geologists and paleontologists and I guess archaeologists in the past. So I put an arrow on Coccoliths and Foraminifera because they're usually the ones that are covering the maps. So I'll just go through very fast each of the time periods. So you can still see vertebrates in the younger time periods, but later on it's going to be mostly marine vertebrates and the protists. And we still have plants from this time. And then what we did was each of the icons actually has a reference to it. So that's where the reference is from, the official reference of the particular fossil where it was reported. So this is for the Pleistocene. It's not a comprehensive one, but it's a pretty large database already. So we're now in the Oligocene. This is beyond 25 million years, the Eocene. And so now mostly it's foraminifera. And then when you get to the older parts in the Mesozoic, the radiolarians come in, especially in the areas of Palawan. Now, what's the plan next? Really to expand the database, and the dream is to have a vetted sort of citizens, I don't know if it's going to happen, but expand the database and make it more publicly available by putting it on the website. We just have to make sure that we can do it in perpetuity so that more people can use it. We already have some of our work, especially the microfossils, are in slides. So we would like to put together and have it more organized reference collection of Philippine index fossils, which are really mostly microfossils. And of course, as Alan said earlier, this is really it's our life's work, and at the same time we love these fossils and we have a passion for them, and we would like more people to be able to enjoy them as much as we enjoy looking at them and making it our life's work. We have a rich heritage here in the Philippines of these fossils. And because earth science is now part of the K-12 curriculum, I think that there would be more opportunities and venues for us to talk about fossils and tell people that they're not really rare, they're just around us. No? In the meantime, not only the index fossil work will continue, but of course all the microfossil work continues, the coccolithophore work, diatom, foraminifer work continues. There are a lot of master students in the lab that are trying to finish to complete their work. In the meantime, the ones who have graduated are now off in the world and spreading the word, I guess, of paleontology. So with that, thank you very much for listening. I hope you're still there. Alas 12 na po. Sana hindi pa kayo gutom. Marami pong salamat.
Maraming salamat, Alyssa. I think you said it right by saying it's your life's passion, life work and passion. And that's what we always want to know from our faculty and researchers in UP. What's our vision, our mission, our plan, and our passion, right? And you have your favorite research topics, but then you're also trying to influence the way our youth will pursue research, education, and research. Okay. Now, you also said that the present is the key to the past, but you and Alan also showed that the past is the key to the present and the future. See, and really, I have so many common interests with you and Alan because I study the present. So we have been studying the bacteria that are the symbionts of bivalves that are in chemosynthetic environments like muddy water. So we published on the biggest bivalve, that's Cuphus polythalamius, polythalamia, that lives on sulfidic waters. And then I was asking you and Alan about the Lithoredo abatania. This is the bivalve, this is shipworms that have bacteria, and we've been able to isolate methanotrophic bacteria. And so we're looking for the methane sea creatures. Okay,